In this video, we consider the relationship between the sample mean and the true mean or mathematical expectation of a random variable. We also introduce sample variance, standard deviation, covariance, and higher moments. Suppose that x1 up to xn are independent, identically distributed random variables with a common mean mu and a common variance sigma squared. The sample mean is then defined to be the arithmetic mean of the capital Xk, in other words, just 1 over n times the sum of the Xk. We denote the sample mean by x bar n. The bar denotes the mean. The subscript n is used to keep track of the sample size. Later on, we will be interested in asymptotic results, i.e. what happens when the sample size n goes to infinity. Right now, our main question is the following. How is the sample mean x bar n related to the common mathematical expectation of the random variables xk? To begin with, let mu bar n be the mathematical expectation, i.e. the mean, of the sample mean. Remember, the sample mean is a random variable, and so we may ask, what is the mean of the sample mean? Similarly, let sigma bar n squared denote its variance. It's easy to show then that the mean of the sample mean, mu bar n, by linearity splits as follows, and each of these terms here is just equal to mu. There are n of them, and so we see that the mean of the sample mean is equal to mu. In other words, x bar n is an estimator whose mean is the true mean. We say that the sample mean is an unbiased estimator of the true mean. Next, let's consider this variance of the sample mean. Remember that the variance of a sum of independent random variables is equal to the sum of the variances. And so it is easy to see that the variance of the sample mean is just sigma squared divided by n. In other words, the variance of the xk divided by n. Thus, though the sample mean has the same mean as the xk, its variance decreases as n increases. Now fix an arbitrarily small epsilon, strictly greater than 0, by Chebyshev's inequality applied to the random variable x bar n, in other words to the sample mean, and noting that its mean is also mu, we see that the probability that the distance from the sample mean to mu is strictly greater than epsilon is less than or equal to the variance of the sample mean divided by epsilon squared. And this is sigma squared over n epsilon squared. Now, though epsilon may be arbitrarily small, as n goes to infinity, this expression over here goes to 0. In other words, the probability that the distance from the sample mean to the true mean is greater than epsilon goes to 0 as n goes to infinity. This means that as n gets larger and larger, it becomes less and less probable that x bar n is a distance of more than epsilon away from the true mean. In other words, it's more and more probable that the sample mean is very close to the true mean. And this is the weak law of large numbers. If x1, x2, etc. are independent, identically distributed draws from a distribution with common mean mu, then the sample mean approaches the true mean. In that sense, x bar n is an estimator of the true mean. In particular, as we've already said, the sample mean is an unbiased estimator, where unbiased means that the expectation of the estimator is the true mean, and moreover it is consistent in the sense that the estimator converges to mu as the sample size n goes to infinity. Next, let's consider sample variance. Recall that the variance of a random variable with mean mu is defined to be the expectation of x minus its mean squared. Thus, variance is just a particular kind of mean or mathematical expectation. It's just the mean of x minus mu squared. Suppose now that x1 up to xn are independent, identically distributed draws from the same distribution as x. In particular, all of them have the same mean mu. We've just seen that the sample mean of the xk minus mu squareds, denoted here by s tilde squared n, is an unbiased estimator of the expectation of x minus mu squared. In particular, it's an unbiased estimator of the variance of x. There is a problem, however. Typically, in performing some random experiment, we will often obtain a sequence of measurements x1 up to xn whose true distribution we do not know. In particular, we do not usually know the true value of mu. The sample variance is then the random variable obtained by replacing the true mean mu with the sample mean x bar n, which is an estimate of the true mean. So the sample variance is defined as follows. We've replaced here the true mean by the sample mean. We've also replaced the 1 over n by 1 over n minus 1. Why the factor of 1 over n minus 1 rather than 1 over n? The reason is that the xk's are correlated with x bar n, which introduces some bias. Intuitively, this is obvious in the sense that if one of the xk's is really, really big, this will influence the size of the sample mean. Mathematically, observe that the xk and x bar are positively correlated. We've dropped the subscript n here to simplify notation. The covariance of xk with x bar, by definition, is the covariance of xk with this sum here. Using the bilinearity of the covariance operator, that reduces to the following. Now the xk's are independent, so the covariance between xk and xj is 0 except when k is equal to j. When j is equal to k, we get the covariance of xk with itself, in other words, just the variance of xk, which is sigma squared. And because of this factor of 1 over n, then the covariance between xk and x bar is sigma squared over n, which is strictly greater than 0. In particular, the expectation of xk minus x bar squared is by definition the variance of xk minus x bar, and that is the covariance of xk minus x bar with itself, and this breaks down as follows. Now the variance of xk is sigma squared. We've just computed the covariance of xk with x bar as sigma squared over n. And 2 slides ago we computed that the variance of x bar is sigma squared over n. The result is that the expectation of xk minus x bar squared is not equal to sigma squared, but sigma squared times 1 minus 1 over n. Hence, if we now take the expectation of Sn squared, as defined on the previous slide, we obtain sigma squared. This means that Sn squared is an estimator of the variance whose expectation is the true variance. In other words, S squared is an unbiased estimate of sigma squared. In particular, the natural estimator S hat squared n, which has a 1 over n rather than a 1 over n minus 1, has an expectation which is slightly less than sigma squared and is therefore negatively biased. Of course, in the limit as the sample size goes to infinity, this bias disappears. We've now defined sample mean and sample variance. Higher sample moments can be defined analogously, although we typically restrict ourselves to the sample moments of the centralized versions. In particular, the sample skewness and kurtosis are defined as follows. The sample skewness is given by this expression over here, where x bar is the sample mean and Sn is the square root of the unbiased estimator of the sample variance that we've just discussed. Similarly, the sample kurtosis is given as follows. Skewness deals with the third moment, kurtosis with the fourth moment. However, these definitions aren't universal. There can be variations. For example, we may use the biased version of the standard deviation that we've just discussed. Many programming languages have these functions built in. But do beware, the above definitions for sample skewness and kurtosis are not universal, And moreover, as we've mentioned before, some programming languages will output the excess kurtosis, i.e. the kurtosis minus 3. Recall that the kurtosis of the normal distribution is equal to 3, and so the excess kurtosis is the kurtosis above that of the normal distribution. Finally, let's consider sample covariance and sample correlation. Suppose that we have a sequence of draws x1, y1, x2, y2, up to xn, yn from the distribution of a bivariate random vector. Let x bar and y bar be the corresponding univariate sample means, and let sx and sy be the corresponding sample standard deviations. In other words, the sample mean x bar is defined as follows, and the sample variance s squared x is defined as follows. The sample standard deviation is just the square root of the sample variance. In that case, the sample covariance is given by the following. And the sample correlation is simply the sample covariance divided by the product of the sample standard deviations, as one would expect.